Okay, so this is work done with a bunch of other people, which you see there. It's done and it was supported by UPMARC, the Uppsala Programming for Multicore Architecture Research Center that we have in Uppsala. And it was joint work with an engineer from VMWare. Those of you that were here last year can see that I talked about something relatively similar. My talk then was detecting concurrency errors using systematic testing, and I actually talked about two different tools and some techniques that we have built at Uppsala, one for Erlang programs and one for C programs, also checking some weak memory models. And I encourage you to look at that talk if you are interested in using tools like the ones that I will show here for detecting errors in your concurrent programs. This talk is not about detecting errors in concurrent programs, but it's related to checking algorithms, concurrent algorithms, whether they are correct. And this was a bit of a surprise to me that we could use a tool that was actually built for finding errors in concurrent programs to also check a concurrent algorithm whether it's correct. I would like to start a bit with some background so that you understand what the tool is doing. This is a tool that, these tools that we have been building at Uppsala are tools for systematic concurrency testing, if you want to use them as testing tools, also known as stateless model checking if you want to verify programs. So this is a technique that tries to detect concurrency errors and verify their absence by exploiting all the possible interleavings that a concurrent program might have, and exploring all the possible ways that concurrent execution can influence a program's outcome. The nice thing about it is it's fully automatic. It has very low memory requirements. Many people think of model checking as being memory hungry. This is a technique that is has very, very low memory requirements. We have been using this also to check some properties of parts of the Linux kernel. But this is not what I'm going to talk to you about today. And it's applicable to programs with finite executions. So the technique is actually conceptually very, very simple. Suppose that you have only one scheduler, you run an arbitrary execution of the program, and then you backtrack to a point where some other thread could have done something different. And from there on, you continue with another execution. And you do this until you have done all the executions. Let's see this on an example. It's a very trivial example. This is not the kinds of programs that we are verifying, but this is the kind of programs that you can understand in a talk like this. Let's say that we have two threads, the green thread and the red thread, accessing two shared variables, x and y, initially 0. And let's say that the programmer has said that the correctness criterion for my program is that in all possible executions, x and y have to be the same have to have the same value at the end of the execution. So we start with one execution. The states here show the values of x and y. And let's say that we pick first the green thread to run. It does its first step. It will update x to 1. And then from that point on, there is no alternatives. We need to pick the next execution, the next step of the green thread, and then the red thread can go. And at the end of the execution, we see that x and y have the same values, so our assertion is holds. So we backtrack to a point where we could have done something different. This is the point 1, 0 in this tree. This will give us now some other thread interleaving, which will also result in the state 2, 2. So again, our assertion holds. And now we pick another alternative and we end up in the state 2, 1. So this we found a place where our assertion is violated. So the exploration at this point can stop at the point where it detects a violation and show this to the programmer. So you can put arbitrary assertions wherever you want in your program, and this model checker, stateless model checker, will check the outcome. Now, what happens if we had some other correctness property, correctness criterion? Let's say that we want in all executions the values of x plus y to be less than 7. So obviously these three executions here hold, the property holds for these three executions, so we have to keep exploring the other alternatives. And actually all the alternatives here will be such that the assertion is satisfied, so we can verify that for all concurrent executions of the program, the correctness criterion that we have in the assertion holds. But notice that now we have to explore all these possible interleavings. We cannot just stop when we find a violation. So this is done in tools, and we have built more than one tool. One of them is called Conqueror, and it stands for finding concurrency errors in Erlang programs or in programs that their model is written in Erlang at least, to either detect the concurrency errors or verify their absence in the way that I sort of showed like that here in the previous slides. Now, in reality, actually, we are not doing something so stupid as I showed in the previous slide. So systematic exploration of all the behaviors of a program doesn't have to actually enumerate all the possible ways that the threads can be interleaved, because these are really, really too many. So we try to explore traces that are somehow different from each other. And you can see how we can sort of do that, that thing if you consider this program here. It's a very, very simple one so that you understand what's happening. Let's say that we have n threads accessing different variables. Obviously, under naive exploration, we have to explore n factorial interleavings, but a moment's thought can convince you that actually you only need to explore only one of them to cover all the possible behaviors. So you can immediately see that there are techniques like partial order reduction that can give you an exponential improvement in the number of traces that need to be explored and still cover all the possible behaviors. Now, of course, this is a very artificial example. Not all programs are so simple like that. So you need to do something better than just handle this particular case. And actually, one of the things that we have done as a group in Uppsala is to come up with some new algorithm called optimal dynamic partial order reduction algorithm that does this sort of thing in a more clever way and doesn't just handle this particular case that I showed you in the previous slide, but also handles other cases. And it's actually the first algorithm for dynamic partial order reduction to be proven optimal, in the sense that it will completely, it will explore only one interleaving per equivalence class in the partial order, and will not even initiate redundant ones. So we have successfully used this algorithm both in Conqueror and in another tool called leadhook to test big code bases like the RCU code from the Linux kernel. So I will not explain the algorithm really in detail here. This is not what this talk is about. But notice that for this example that we had before, the gray nodes will not be explored at all. And you can sort of guess why these gray nodes will not be explored, because they end up in final states that are similar to some other final state. While for soundness, you have to actually explore all the other possibilities here, because they all lead to different final states. Okay, so if you had the correctness criterion that checked something special for this final stage, you really have to explore all of them. Now, on top of that, you can put some bounding techniques. You can say that I don't want to actually check my whole search space. I can only check a subset of it, just to see if my property is violated in this subset. So this is a very good technique for testing programs. Is not a very good technique for verifying programs. You can only verify up to a bound. But in general, you want to, when you talk about verification, you actually want to explore all the possible interleavings. But if you want to just quickly check and find violations in your correctness criteria, then you can use some bounding technique. And let's say that we have as criterion here how many times threads can be preempted and only allow up to certain number of preemptions. Let's say that we are very strict and we only allow that threads are never preempted. In this case, you need to explore only the 2 out of these 6 interleavings, because you never preempt a thread. You never allow a thread that can run to be preempted by another one. While with a preemption bound of 1, you would not explore these 2 cases. So you can actually use this idea and say that I will start my testing with a small number of preemptions or a small number of whatever your bounding is, and gradually increase it until I come to the verification point. So this is actually the background for what I really want to present, which is a case study that we have done together with engineers at VMWare to verify algorithms for some new replicated database they have done. But before talking about that replicated database, I will talk about the basis of that, which is called chain replication. It's a paper at OSDI 2004. It's a way to have a replicated database with some particular properties. So in this particular example, we have three servers, the blue, the orange, I guess, and the magenta, or whatever color is that, that are in a chain. So all the requests, all the write operations start from the left and get propagated towards the tail. So when we want to write a new value in the database, we start first sending it to the head. The head will send it to the next one in the chain, the next one, until it goes to the tail. And then the tail will say, okay, now every replica has this value. So all the read operations in that scheme, they go to the tail brick if you want to preserve linearizability. So you need to you can only read from the last one when all the replicas have this particular value. So you can do sequential read at the tail, linearizable read actually everywhere in this case, and you can be dirty and say I will read wherever, and you can read wherever. So this thing works, obviously, and it also handles the case when something goes bad, and this is the chain repair problem. So let's say that we have a number of servers, say 3 of them, and something bad happens and one of them crashes. So what we want to do in the chain repair is to repair this chain, i.e. bring the new server back. So one naive way of doing this sort of thing is to say that we'll stop all the servers, and we are going to copy the tails update history to the repairing node. So we're going to attach now a new server, and we're going to copy everything from the new tail, well actually it was also the old tail, to the new server. So that will restore the history, and things will work from that point on. And then we restart with all nodes in a new configuration. Now, the problem is that you actually don't want to do that sort of thing, because the whole point of having this scheme is so that you have availability of the servers. So you want to actually repairing the chain while the things are running. So a better repair method places the repairing node directly on the chain, and all the reads now go to the old tail. And when the repair has happened, then you can switch the tail, and things will work. Now, this is vanilla chain replication, but the system we were looking at is actually a system called CORFU. And CORFU actually doesn't stand from the island which is in Greece. It stands for something that you can look it up, but this CORFU DB was initially done at Microsoft Research. These days is mostly, it's an open source project, but mostly is continued at VMWare. So this uses ideas from chain replication, but there are some changes. Obviously, otherwise I wouldn't call it differently. So there are some changes, and actually you don't really need to understand the changes, but you need to understand that there is a write-run semantic, so it looks like they are immutable. It's an immutable writes here, and the system is a bit more complicated because it also associates stuff with epoch numbers and stuff like that. Now, so this paper, or actually this collaboration, started by some engineers at VMware trying to investigate, to design methods for chain repair in this CORFU system. And they sat around a whiteboard or a room discussing this thing and said, okay, let's try to come up with a repair scheme that places the the new server at the tail. Let's start the repair at the tail. And they actually came up on the whiteboard with an example where this one breaks. And the example is very, very complicated, so I will not actually show you here why this thing breaks. I have 18 slides for those interested to show you in detail how this thing breaks, but trust me, this doesn't work. So what they did then is they said, okay, let's come up with a new example, with a new algorithm. Let's add the new server at the head. So if it doesn't work at the tail, let's put it at the head and see if it works. And actually, they couldn't come up with any example that showed why this one doesn't work. Until they wrote this sort of thing in Erlang, they modeled the system in Erlang, and they used Conqueror to check whether there is any possibility of an error. So when you use these things, of course, there are possibilities in having a wrong model also. And as a matter of fact, that's what happened. But actually, there is a bug, even in the correct model. But the engineer there was particularly happy about it and tweeted it, and that attracted our attention. And then we collaborated a bit with this. So this is how we modeled CORFU in Erlang. So we try to have the first thing we tried is to have an initial model that does the following things. We are modeling now a chain repair. So we want to have a number of servers that undergo a chain repair to add one more server to the chain. So the minimal configuration for checking everything that everything goes okay is to have either one server or two servers. And why do you need one or two is with one, you can add it either to the tail or to the head. And with 2, there is also the possibility of adding the new server in the middle. Okay, so you can convince yourselves that this is, you actually need to check both one, the case of 1 and the case of 2. And concurrently, you have clients that try to write new values to the key, to the same key. This is a key value store. You try to write new values. You need 2 clients because they need to check, you need to have 2 different values so that you can check which one is read. And the 3rd client tries to read the value of that key. Okay, so that explores all the possibilities of what can go wrong here. So the servers and clients are modeled as Erlang processes. Erlang is a concurrent language that has processes, so it works very nicely to model these entities as Erlang processes. All requests that are happening here are modeled as messages, so they are totally asynchronous, so you check all the possibilities of what can happen. And you use a bunch of processes in the model. A central coordinator that works like the orchestra maestro or something like that. The servers that are involved in the process, the 2 that had survived and the new one. The layout server process, a CORFU reading client, two writing clients, and the layout change and data repair process that goes on. And you check 2 different correctness properties. The one is immutability, because CORFU is a database that requires immutable values. So once a value has written in a key, no other value can be written in it. And linearisability, that if a read sees a value for a key, then subsequent reads for that key also must see the same value. So these are the 2 correctness criteria that you model, that you request, that you require. So with that model, we investigated 3 repair methods. The one that we knew it was buggy, adding the chain repair node at the tail. One that initially we did not know whether we could add it at the head, and also adding the repair node in the middle. In the middle, you have to actually check 2 possibilities. One where you are left with 2 healthy servers, or you really add it in the middle, or you are just left with 1 healthy server, so you logically split this healthy server into 2. So you, checking all the possibilities, you actually need to do that sort of thing. And here's what we got. So with bounded exploration, remember that I showed you the preemption bounding before, but Conqueror uses some other kind of bounding, but it doesn't really matter. The tool finds very, very fast that the 2 first methods are buggy. So adding the new server at the tail doesn't work, and adding the new server at the head doesn't work either. And it explores a small number of traces, a small number of different interleavings, 638 in the first case, 65 in the second one, and actually it finishes in less than a minute. Now, with the middle, adding the new server at the middle, it explores 1,200 and change traces and stops in a bit more than a minute. But that tells you nothing. Okay, it just tells you that in those traces there is no problem. But for testing and finding a bug is easy. Verifying it is very hard. So you need to go to unbounded exploration. And with unbounded exploration, you see that things go actually a bit wild here. So you cannot find you find the bug in the first case only after 144 hours. And in the third case, you explored more than 30 million interleavings and it doesn't stop after 750 hours. So that's where you need to take into your hands the model, first of all. So we did two changes in the model. One is to do a conditional write, conditional read, so we don't have to read the two values if they cannot result in violation. So for example, if nothing has been written there, you don't have to do all the two reads, just an example. And we also converted the layout process to a net table. This is for technical reasons, you have to do that sort of thing. I will not explain right now why. So, but you have to change the model a bit. The other one you have to do is we gave us an opportunity to do an optimization in the tool itself to treat the blocking receives whose message patches were all known specially. And this also gives you an exponential speed up when this optimization is applicable. I will not bore you with the technical details. We can talk about these things offline in the break. But with those changes, two changes in how we did the modeling and one change in the algorithm that the tool is using, we were actually able to verify after 48 hours and after a significant number of traces, as you see there, that actually the third method is safe. There is no possibility to add a server in the middle in CORFU and some bad thing can happen. And also method number one, the one that did not finish, that needed, if you recall, 144 hours to finish, now finds the error in just 19 seconds. Okay? So here is a table that is probably uninteresting, so I will skip it. It just shows you what the effect of each of these changes in the refinements and the optimization do on their own. But actually is the case where you find the error, so how fast you find the error is also depending on your luck, or actually on the way that things are checked. So it's not particularly interesting really. But here's the take-home message. Stateless model checking tools like Conqueror or like leadhook, another tool that we have developed, can not only find errors in concurrent programs, possibly with weak memory models, if you are interested in that sort of thing, but also can be used to check new algorithms, new concurrent algorithms and protocols. And they can detect bugs in them quite easily, and it takes a bit of effort actually to make them verify that everything is correct. But once you have verified this, remember here we are talking about a case where the engineers were actually building the algorithm. They did not know whether it was correct. As a matter of fact, they thought that the second method would work, but the tool found out a case where it did not. On the other hand, knowing how to write a correct and efficient model can be quite challenging. So it was actually a very nice collaboration because we helped them refine the model also and still having correct. And one thing that bothers me a bit is that actually it's not very clear how do we explain to users why their correct model are hard to verify. Why one correct model is considerably harder to verify than another correct model. With that, I would like to thank you for your attention and take one or two questions before the coffee break.